All right, hello today. This is Matt Dean with A Plus College Ready, and today we're going to be looking at a set of Unit 7 practice problems. Unit 7 in AP Physics 1 covers torque and rotation. So we're going to start with this problem about a seesaw. A uniform board of mass 30 kilograms and length 3 meters is used to make a seesaw. A boy of mass 52 kilograms sits at one end of the seesaw. How far from the boy's side of the board should the fulcrum be placed in order to balance the seesaw? No other masses will be used. So first of all, it's always a good idea to try to draw this out. So my drawings are terrible, but let's say that's the board. And remember, the whole length of that board is 3 meters. I'm going to put a dot here in the middle. There's the middle of the board. And we're going to think of that as the center of mass of the board. And what that means is we can think of all of the mass of that board as acting at that point. Since we're going to put the boy on one side, let's put the boy over here on the left. I'm just going to call that B. Remember, the boy has a mass of 52 kilograms. Now, you guys, I hope, know that to balance this thing out, the fulcrum is going to have to be somewhere in here. Because what should happen is that the torque caused by the boy over on the left, which is going to be a counterclockwise torque, is going to have to be equal but opposite to the torque caused by the center of mass over on the right, which is going to be a clockwise torque. So let's set up an equation for that, sort of derive out an equation. So the torque of the boy, remember, torque is force times length of lever arm, or some people call it radius. So the force is going to be the weight of the boy. So the boy has a mass of 52 kilograms. We need to convert that to weight by multiplying it by G. And we're going to call the distance between the boy and the fulcrum, we're going to call that X. So that's got to be equal to the torque caused by the center of mass. Well, all the mass of the board acts at that point. Its mass is 30. We multiply it by G. And those should be meters per second square, by the way. Now, the length, therefore, this is where you got to think a little bit. The whole board from end to end is 3 meters long. Well, we're really not so concerned right now about the whole board. We're concerned about the distance from here to here. Well, the center of mass is halfway in the middle of the board because it's a uniform board. So that means from the boy's end to the center of mass, that's 1.5. So if we call this distance X, then the distance between the fulcrum and the center of mass has to be 1.5 minus X, the rest of that half of the board. All right, so now we just have to solve out this problem. First of all, I'm going to cancel the 10s on both sides. So that's going to leave me with, I'm going to make some space down here at the bottom. Actually, I'll just try to do it right here. So that's going to leave me with 52 kilograms times X over on the left. And then I have to distribute, the 30 up top. So we're going to have 30 times 1.5. So that would be 45. And that's kilograms times meters minus 30 times X. All right, I'm going to add that 30 to both sides. So that's going to give me 82 kilograms times X equals 45 kilograms times meters. I'm going to divide both sides by 82. And when I do that, I end up with X equals 0.549 meters. This question asks me how far from the boy's side of the board should the fulcrum be placed. So that is, let's go back to the picture here for a second. Remember, we had the center of mass right here. We had the boy over here, and we had the fulcrum here, and we called this distance X. So this is our answer. Now, sometimes they'll ask you how far from the center of mass should the fulcrum be. If they'd asked you for that, then you would have went 1.5 minus 0.549, and you would have gotten your answer there. All right, that's problem one. Let's go ahead and look at problem two. It's very similar. Here's problem two. A uniform board of unknown mass is used to make a seesaw. A buoy of mass 35 kilograms sits at one end. It is experimentally determined that the fulcrum must be placed 0.756 meters from the buoy in order to balance the seesaw. No other masses are used. What is the mass of the board if the board is 3 meters long? So again, same basic setup. Here's our board. It's 3 meters long. Here's the middle, our center of mass. We're going to put the buoy over here. And it tells us in this case that we put the fulcrum 0.756 meters from the buoy. And we want to know what is the mass of the board. All right, so here's something that we need to start with. We know the distance from the center of mass to this other end over here is 1.5, which means the distance from the fulcrum to the center of mass is 1.5 minus 0.756. So let's do that math, 1.5 minus 0.756, and we end up with 0.744. So again, that's the distance in here. That's the distance from the fulcrum to the center of mass. So now we're going to do the same basic setup we did before. The torque caused by the buoy has to be equal but opposite to the torque caused by the board, or we'll say the center of mass. So we know for the buoy, he has a mass of 35 kilograms times G to get a force. So that's the force. And then the radius, or the lever arm distance, is the distance from the buoy to the fulcrum, which the problem told us is 0.756 meters. It's got to be equal to the torque caused by the center of mass. We don't know the mass of the board, but to convert it to a force, we have to multiply that by G. And then we have to multiply that by the lever arm distance, which is the distance from the center of mass to the fulcrum. We found that to be 0.744 meters. All right, so we're essentially going to cancel out the tens. We'll divide both sides by 0.744, and we'll end up with something like this. 35 kilograms times 0.756 meters divided by 0.744 meters is equal to the mass of our board, the mass of our center of mass. And when we do that math, let's do it right here real quick. So 35 times 0.756 divided by 0.744. And it's looking like we get about 35.6 kilograms for our mass. All right. One term I'll introduce here. If we balance out a seesaw like that and the torque on one side is equal but opposite to the torque on the other, and there's no rotation going on or no acceleration, angular acceleration going on, we can say that the board is in static equilibrium. And we could say rotational equilibrium in this case too. It's not moving laterally, it's not rotating. It's static equilibrium. It's not rotating, it's in rotational equilibrium. All right, let's move ahead to practice problem number 3. This one's a quicker one. So we have a uniform meter stick set onto a fulcrum at the center of the meter stick. So it's right in the middle of the meter stick. And you can see the fulcrum here is our blue triangle. If a force of magnitude 2F is applied in the upward direction at the indicated point, at which labeled point must a downward force of magnitude F be applied to keep the meter stick in rotational equilibrium. So notice what it says here. At what labeled point must a downward force? Now, a lot of you would be quick to jump in and say, well, the force is over here. So the downward force has got to be over, say, here. A lot of you would think, well, this is 1 unit away from the center, so this one's half as big a force. It's got to be 2. But then you look at it and see what kind of torque that's causing. This force over here on the left is causing the board to go this way, clockwise. Well, if we put the force here in location D, like we currently have labeled, it would also cause it to rotate clockwise. So that's not going to cause rotational equilibrium. That's going to make it accelerate more. If we were to put it at A, if we put a downward force here, it would also cause a counterclockwise torque. It's not what we need. If we're going to use a downward force, it's going to have to be over here on the left side. And since our force of magnitude 2F is only 1 unit from the fulcrum, so that gives us and let's just say these units right now are meters just to keep it easy. So our torque caused by that force, and we'll say torque caused by the 2F force, would be the force times the distance. Well, we need the same torque, opposite direction. So we'll say torque of F, which is the magnitude of our new force, it's going to be the force times the distance. It's got to be, the only way to even it up with this is to make it be 2 times as far from the fulcrum, which means it's got to be right here. So our answer is C. If we put a downward force here, it's going to cause a counterclockwise torque, whereas this 2F force is causing a clockwise torque. And since their magnitudes are the same, but their directions are opposite, this thing is going to be balanced. It's going to be in rotational equilibrium, which is what we're looking for. So answer C is correct. All right, let's move on to number 4. So the diagram included above shows a top view of an individual of mass M on a merry-go-round of mass 4M. It's rotating in the clockwise direction. Assume that the platform rotates with 0 friction. Which of the following describes an action of the rider that will increase the angular momentum of the rider merry-go-round system? So let's think of this whole thing as a system. What can the rider do to increase angular momentum? Well, remember that angular momentum, L, is equal to the moment of inertia times the angular velocity. Well, no matter what this guy does, he can move around and he can change his mass, but he's not going to change the whole system by moving around. He could change the rotational inertia of the system, but if he moves out, for example, and makes the rotational inertia go up, then the velocity is going to go down because the angular momentum is conserved in this closed system. So my point is, he can change both of these variables. He can make, by moving around, by moving further out or closer into the middle, he can make the thing speed up or slow down. That's happening because he's changing I. But when he does that, if I goes up, the angular velocity is going down by the same amount. Point being, there's nothing he can do in this case to change the angular momentum. It's conserved because he's working in a closed system. The only way that he can change that angular momentum is by having some kind of external net force or net torque. And just him, and since he's part of the system, he can't apply that in this case. So D's our best answer. Let's move on and look at problem 5. Same setup. So again, we've got mass M, merry-go-round of mass 4M. We're still rotating clockwise. Which of the following describes an action of the rider that will increase the angular velocity? So again, remember, this is really the equation we're working with. And we're working with something that will make this go up. And we know that by increasing, if the velocity increases, that means the moment of inertia has to go down because this quantity is conserved angular momentum. So most of the moment of inertias look something like this. mr squared. That's the equation for most moments of inertia. There's going to be usually some kind of fraction out here in front of that, depending on the shape that you're dealing with. But for right now, mr squared is enough. We can't change the mass of the system. But what we can do is change the radius. We can change where some of that mass is at. And the only way we can make the angular velocity go up is by making the moment of inertia go down. And the only variable that we can control in this equation up here to make that moment of inertia go down is r. And if we move mass closer to the center, that's going to decrease I and therefore increase angular velocity. So we're looking for the rider is going to move toward the center of the platform. That's going to decrease the I and therefore increase the angular velocity. So choice A looks good. All right, here's problem 6. A little bit more math involved in this one. So the wheel on a car has a rotational inertia of 4 kg/m squared. At the moment that the wheel has a counterclockwise angular velocity of 8 radians per second, an average counterclockwise torque of 4 Newton meters is applied for 4 seconds. What is the angular velocity of the wheel at t equals 4 seconds? All right, so here's what we've got to deal with here. Really, this is going to be like an impulse momentum kind of problem. If you remember back to linear momentum, you had change in momentum was equal to impulse. And if you were doing that in terms of linear things, it was mass times change in velocity, change in momentum, is equal to force times change in time. That's impulse. But when we do rotation, a little bit different. Instead of mass, we deal with the moment of inertia, I. And instead of delta V, we're dealing with angular velocity, like so. It's not just force that causes the angular velocity to change, it's torque. And times the same. So this is the equation that we're looking for. And really what we need to solve for here is the change in angular velocity. So let's divide both sides by I and end up with this. We plug in some numbers. Our torque was 4 Newton meters. We're applying that torque for a time of 4 seconds. And we have an rotational inertia of 4 kg/m squared, which means our change in angular velocity is positive 4. And notice that everything here is going to cancel out. And we're going to end up with radians per second is what we end up coming up with for a unit. So we end up with a change of positive 4 radians per second. Now, some of you are going to be tempted to mark that answer. Not correct. We just found a change in angular velocity. The question asks, what is the angular velocity at 4 seconds? In this problem, we started with a velocity of 8. We changed the velocity by plus 4, which means our new velocity is now 12 radians per second. And that's practice problem number 6. All right, let's move on to number 7. So here's 7. Similar kind of problem. So it says we have a rotational inertia of 4, counterclockwise angular velocity of 8, torque of 4, applied for 4 seconds. What is the change in angular momentum? All right, so remember, change in momentum, and we're going to do it in terms of linear first, is equal to impulse. Remember that change in momentum in terms of linear things is m delta v, and impulse is f delta t. When we're talking about rotational stuff, the m's replaced with the moment of inertia. We put in angular velocity instead of linear velocity, and that's equal to the torque times the change in time. Either way, this is the change in angular momentum, the circled portion of my equation. Now in this problem, I know the I, I don't know the change in angular velocity, although I really do because we calculated it in the last problem. But let's pretend we did this problem first. We don't know that. So if we don't know that, what we do know, though, is everything over here. And we know these two sides are equal. So we know the torque. The torque is 4 Newton meters. And we know the time, 4 seconds. And we know that that quantity, torque times change in time, is equal to our change in angular momentum, which means our change in angular momentum is 16. And it's 16 kilogram meters squared over seconds. So our answer should be A here. Again, similar problem to what we had in the first one, but you've got to know what your variables stand for. I times change in angular velocity, that's the change in angular momentum. And that is equal to the impulse. All right, here's problem number 8. So the Earth moves in an elliptical orbit around the sun. The mass of the Earth is much less than the mass of the sun. At the instant illustrated in the diagram above, the Earth is moving away from the sun. How does this affect the magnitude of the angular momentum of the Earth with respect to the sun? And really the question is, as we're talking about angular momentum, remember that angular momentum is a conserved quantity. So as the Earth moves away from the sun, let's think about it this way. I is going to be going up, so this gets bigger. But as I gets bigger, the angular velocity has to get smaller because these two things still have to multiply together to give us the same angular momentum. So point is, as the Earth moves away, it doesn't change the angular momentum. It changes the velocity because as I goes up, that means the velocity goes down. This doesn't ask us the velocity, it asks us for the angular momentum. Our answer is no effect. It does change the velocity. It does change the moment of inertia, but it doesn't change the angular momentum because it's conserved in this case. All right. Practice problem number 9 coming up. So this one says the figures below illustrate a door hinged on its left side. So hinges are over here. The door is initially at rest and is free to rotate in either direction. It's one of those doors that can swing either way. Assume that there is negligible friction at the hinges. The arrows indicate forces of different magnitudes applied to the door at different locations. In which situation will the angular speed of the door increase at the fastest rate? All right, so first of all, you got to think about this. Important equation. Torque is equal to the moment of inertia times the angular acceleration. So bigger torques mean bigger angular acceleration. Faster changes in angular speed. That's really another way to look at it, angular acceleration. So really what this question is asking us is in which one of these cases is there going to be the biggest torque? So if we look around and see what we've got here, let me move this bar out of the way a little bit. So we know that torque in this case is going to be F times R. So a bigger F causes a bigger torque, a bigger R causes a bigger torque. And what we can see is in choice C, we have the biggest force, 2 times F, and that force is as far away from the hinges as it can be, which means we've got the biggest R. So in choice C, we've got the biggest force and the biggest radius, and therefore the biggest torque, and therefore the biggest angular acceleration, or the biggest increase in angular speed of the door. So we're looking at problem C, or choice C, as our answer. All right, here's question 10. First of all, I'll say that this is one of the questions that it's like the last 4 or 5 questions on the AP exam where you have to choose 2 correct answers. You have to get both of them right to get any credit. So you've got to be really careful when you're answering these questions. Notice it says a fulcrum is placed at the center of mass of a uniform meter stick. A mass is placed on top of the meter stick to the left of the fulcrum. A child is asked to place a second mass with less mass than the original mass on the meter stick, so it'll balance out horizontally. Which of the following quantities are needed to determine where the second mass should be placed? All right, well, we know for this problem to work that the torque over here has got to be equal but opposite to the torque over there. And we know that torque is force times radius. Well, the force is going to be the weight of both of these masses. To find that weight, we've got to know the mass of each mass. So that looks like a good choice. It'd be important to know those. In this case, the mass of the meter stick doesn't really matter so much. And the reason it doesn't matter is because the fulcrum is in the middle. It tells us we put it at the center of mass. So that means there's as much mass of the meter stick over here as there is over here. So we do not need to know this. The width of the meter stick, that it could be a really narrow one, it could be a really wide one. That doesn't really help us. But what does matter is this distance. How far is it from the fulcrum to this first mass? That would be this R. And if we know this weight and this R and this weight, then we ought to be able to calculate that R. So our choices here, A and D, look good. And again, it's just that whole idea, if we want to be in rotational equilibrium, the torque on one side has to be equal and opposite to the torque on the other side. All right, question 11 looks like this. So a system consists of a merry-go-round rotating on a frictionless axle and a small child running toward it as shown above. The outer edge of the merry-go-round is moving at a linear speed v, and the child is moving at a speed of v over 4. The child hops onto the merry-go-round. Notice it says right here, important, ignore any torques or forces that may have occurred as the child pushed off the ground. How does the angular momentum of the system after the child gets onto the merry-go-round compare to the angular momentum of the system before the child gets on the merry-go-round? Important. We defined the system in the beginning of the problem as the merry-go-round and the child. That's the system. And we know that the angular momentum of that system before is going to be the same as the angular momentum of that system after. Angular momentum is conserved. Since the child and the merry-go-round are both part of the system, there's no external forces acting on the system. Therefore, the answer has to be D. Angular momentum is conserved because there's no external torques acting on this system. Now, if we hadn't defined the child as part of the system, it'd be a whole different problem. And the angular momentums would change. But in the beginning of this problem, we defined the system as the merry-go-round and the child, and therefore the angular momentum is conserved. All right, let's move on to question number 12. Question 12 looks like this. It says, 2 robots sit on a rotating turntable that is spinning in the counterclockwise direction. Assume there is no friction in the bearings of the axle. How does the angular speed of robot A compare to the angular speed of robot B? All right, so remember that angular speed is really the angular displacement over the time. And let's think of this in terms of, we can think of it in terms of degrees or revolutions or radians. It doesn't matter. We usually work these problems in terms of radians. When B goes around one full circle, 2 pi radians, A also goes around one full circle. Now his circle's smaller, but it's still, in terms of radians, it's the same amount of radians. So they're going to have the same angular displacement in the same amount of time, and therefore their angular speeds, their angular velocities are the same. So C looks like a good answer here. Now, where this gets maybe a bit more complicated is when we look at the next one. So the next one says, same problem, but this time it wants to know the linear speed. And what we've got to think about here is that B's on the outside. So he's making these big circles. Whereas A's on the inside, he's making smaller circles. So think of it this way. Think of it as if we took those circles and cut them and then stretched them out into straight lines. B's straight line is going to be much further than A's straight line. B is going further linearly in the same amount of time. That means he's going faster in terms of linear velocity. Now, another way to think about that is that we could take the linear velocity is equal to the angular velocity times the radius. So B has a much wider radius than does A. Either way, B's velocity is faster than A's. The question asks, how does the linear velocity of A compare to B? So A's velocity is less in terms of linear speed than B's is. So B looks like a good answer here. All right, let's look at 14. Same setup. So refer to those previous two problems about the robots. Robot A begins to walk in a circular path in the opposite direction of the turntable's rotation. How is the magnitude of the angular momentum of the turntable, not the system, affected? So let's go back to the picture here. So is rotating this way, but A starts walking this way. So for A to walk this way, he's got to push on the turntable the other way. And that's where it gets a little bit confusing here. Let's again think back to the picture. For A to go this way, he's got to push this way on the turntable, which turns out it's in the same direction it's already rotating, which means there's going to be a net force, a net torque acting in the same direction as the rotation of the turntable. And since that rotation is in the same direction as the net torque acting on that turntable, it's going to actually get faster. So the magnitude of the angular momentum of the turntable is going to increase. Now, the angular momentum of the system, if we think of the system as being the robots and the turntable, it's not going to change. It's going to be conserved. But in this case, we were only looking at one piece of our system, which was the turntable. And A looks like a good answer for that. All right, let's move on to 15. So in 15, we've got a wheel with an unknown rotational inertia, free to rotate about a central axis. It starts out at rest. Boy wraps a rope around the wheel, and he pulls the rope with a force sensor, and he causes that wheel to rotate. He records the tension in the rope and the time for which the rope was pulled. So essentially how long he was applying that force. Without measuring the wheel's final angular speed, can the boy determine the magnitude of the wheel's angular momentum? And the answer here is he can. And what he needs to know is essentially this. Remember that angular momentum is, that's one way to think about angular momentum. And we could think of change in angular momentum like this. And we know that change in angular momentum is equal to impulse. So here's the thing. If the boy knows the force that he's pulling on the rope with, that force is part of the torque. He knows the radius of the wheel, R, and he knows how long he applies that torque for. So if he knows he can calculate the torque, he knows the time, that will give him the change in angular momentum. And we're starting at rest, which means originally angular momentum 0. So choice B looks like a good choice here. The boy can measure the wheel's radius, he can calculate the torque, and therefore multiply that by the time and get the change in angular momentum. B looks like a good answer. All right, now let's look at 16. This again is one of those select two answer kind of questions. See if I can move this around a bit. So 4 solid cylinders, each of mass M, are attached on the left end to a table. And that's what the orange dots represent. So that's like their pivot point. And they're free to rotate around that pivot, no friction. Forces are exerted on the cylinders with different magnitudes and in different directions as shown. The rotational inertia of a cylinder of mass M and length L about the end of the cylinder is 1/3 mL squared. In which cases do the cylinders experience equal angular accelerations? Select 2 answers. All right, so here's the deal. So first of all, torque is equal to force times length. And remember that we also have this sine theta component. And that's essentially the angle between the lever arm and where the force is applied. So that's our torques. We also are going to need to think about this equation right here. Torque is equal to moment of inertia times angular acceleration. So remember, what we're looking for here is in which cases do the cylinders experience equal initial angular accelerations. So first of all, let's calculate torques. So for A, the torque would be the force times the length. For B, torque would be the force times the length. Notice those two are the same. For C, torque would be the force, 2F, times the length, 2L. Notice that one's not the same as that one up above. And then for D, and notice that these forces are applied at a 90-degree angle to the lever arm. The sine of 90 is 1, so it doesn't really matter so much there. On this one, though, the force is applied at a 30-degree angle to the lever arm. So we're going to need to go torque is equal to the force, 2F, times the length, L, times the sine of 30. Well, the sine of 30 is 1/2, which means the torque is going to end up being F times L. So those are our torques. Now, for choice, well, let's look at our choices now. For A, if we calculated I would be equal to 1/3 M times the length squared. All right. For this next one, I is equal to 1/3 M times our length here is 2L. So 2L squared. Down on C, and I'm going to write it over here on the side. I equals 1/3 M, and our L is 2L squared. And then down here at the bottom, I equals 1/3 ML squared. Now remember, we're looking for equal angular accelerations. So if I take this equation and solve it for angular acceleration is equal to torque divided by moment of inertia. So we need to look at which one of these 4 setups are we going to end up with torque over I being the same. And I think if you look at these closely, you're going to see that it's going to be C and D. For example, on C, the torque is 2F times 2L. So that would be 4FL. And I is, let's see, 1/3 M times that 2L gets squared. So that's going to be 4L squared. All right, so that's for this one. Now we could do a little simplification of this. So we could cancel out one of these L's. We could cancel out the 4. And then we could flip the 1/3 to the top. So we end up with, for C, 3 over F over ML. 3F times over ML. That's the simplification of this for picture C. Now, if we did the same thing for D, the torque on D was F over L. And the moment of inertia was 1/3 ML squared. So again, we can cancel an L. And then we can flip this 1/3 over to give us 3 times F over ML. And notice that and that are the same. You're only going to get that same ratio on C and D. Remember, you got to get both of those to get the right answer. Choose 2. All right, problem 17 looks like this. The angular momentum of a rigid body rotating around a fixed point as a function of time is illustrated in the graph. Which of the following statements are true? Select 2 answers. So this is another one of those select 2 kinds of things. I want you guys to take just a moment and look at it. Notice that our graph is angular momentum against time. And what I want you to think about is angular momentum, remember, is I times angular velocity. When we find the slope of a line, we're dividing y by x. So if we took our y, our angular momentum, and we divided it by time, what we would end up with is that. And notice that angular velocity over time, that's angular acceleration. So something like so. So if we look a little closer at this, which of the following statements are true? Well, the angular velocity, not true. It's changing. But the angular acceleration, it is true. Because remember, this slope represents angular momentum over time, which is that. So yes, angular acceleration is going to be constant. And then finally, the other one that looks good here is D. The net torque applied to the body is constant. We know that because torque equals I alpha. If this is constant, then that torque is going to be constant because this thing is a fixed body. It says it's telling us it's rigid and it's fixed. We can't change the I. We can change this. We can change that. If one of those is constant, that means the other one has to be constant. So the only way this works is if you choose B and D. All right, let's go to 18. This one's a little more complicated. So a solid disk whose plane is parallel to the ground. So again, you can think of this almost like a merry-go-round. Spins with an initial angular speed. 3 identical lumps of clay are dropped onto the disk at locations 1, 2, and 3, one at a time every 10 seconds, but not necessarily in the order of 1, 2, 3. So it could be random. Each lump of clay sticks to the surface of the disk, slowing the disk rotation. A table of the angular speed of the disk as a function of time is included below. So this table. Based on the data presented in the graph, which of the following lists the points in the order in which the blocks are dropped onto the disk? All right, so here's the thing. We know that by dropping these blobs of clay onto the disk, that's going to increase I. So I is going to start out small, and then every time we get a blob, I gets bigger. And when I gets bigger, the angular speed is going to decrease. Well, what determines I is the mass of the blobs, which it tells us they're identical, so they all have the same mass. But the other thing that determines their effect on the eye is where they are. How far are they from the center of rotation? So a blob of dropped at 0.1 has a much bigger radius than, say, a blob dropped at 0.2. Remember, these moments of inertia usually are proportional. Let's make that be proportional to mr squared. So a pretty small difference in the size of r can cause a pretty big difference in the size of I. Point being, the further out, the further toward the edge the blob lands, the bigger effect it has on I, and therefore the more it causes the speed to decrease. So let's look. Our first blob gets dropped at 10 seconds, and the speed drops by 2.5. Our second blob gets dropped at 20 seconds, and our speed drops by 5. Our third blob gets dropped at 30 seconds, and our speed only drops just a little bit, 1.25. So our biggest change in speed happens here at the 20-second mark, right? Because the change of 5 happens there. Well, that's got to be object 1, because it's the one that's the furthest out. It's going to cause the biggest increase in I, and therefore the biggest decrease in the speed. So 1 has to hit first. Well, that's telling me that, wait a minute, something's not right there. Nope, sorry, that's not right. 1 doesn't hit first. 1 hits second, right? 1's the second one to drop. It's because of the biggest change. So this is going to have to be our right answer. The second biggest change happens at 10 seconds. Well, that's got to be where 3 hits, because it's the second furthest from the radius. And then 2 hits almost right at the center of rotation, maybe just a little bit to the left. It causes very little change in I, and therefore very little change in the angular velocity. So object 3 hits first, causes a little change. Object 1 hits next, it causes a bigger change. And then object 2 hits last and causes a very tiny change in the angular speed. All right, that's problem 18. Here's problem 19. A wheel of radius 0.5 and rotational inertia of 4 kilogram meter squared spins on an axle with an initial angular speed of 4 radians per second. Friction in the axle exerts a torque on the wheel, causing the wheel to stop after 8 seconds. What is the magnitude of the net torque acting on the wheel? All right, so this is another one of those where we've got to use change in angular momentum is equal to impulse. Remember, the change in angular momentum looks like this, and the impulse looks like this when we're talking about rotation. We're looking for the net torque. So let's solve this for t. So I'm just going to divide both sides. This should be delta t right here, by the way. Going to divide both sides by the time. Going to look like this. So first of all, my I is 4. Going to multiply that by the change in angular velocity. So we start off with an initial angular velocity of 4, and the wheel stops, which means the change in angular velocity has to be -4 radians per second, because it goes down to 0. Remember, to find change in anything, you take the final minus the initial. So our final velocity was 0. Our initial velocity was 4. That's how we get the -4. All right, we're going to divide that by the change in time, 8 seconds. So we end up with 4 times -4, -16, divided by 8. We end up with a net torque of -2. It's going to end up being Newton meters. Notice this only asks for the magnitude. So our answer here is C, 2 Newton meters. All right. Problem 20 looks like this. Looks a little bit more complicated. A horizontal disc is free to rotate about an axis at its center. The arrows in the diagram below represent forces of equal magnitude that are exerted on the edge of the disc in the directions indicated. Which of the following correctly ranks the magnitude of the torque about the axis exerted by each force? Well, here's the thing. Notice that C and D are both exerted along a radius. So the angle, remember our torque is force times radius times sine theta. Well, both of these are along the radius, which means this theta here is 0. And the sine of 0 is 0. So both of these essentially exert no torque on the system. So they're going to be the smallest, and they're equal to each other. So the torque of C and D are equal, which means it's got to be either this one or this one. Well, we look up here at the next one. Let's just draw in sort of an imaginary radius like this. Draw in another imaginary radius like that. Notice that B essentially acts at a 90-degree angle to that radius. Whereas for A, that angle is much less than 90. Definitely not a 90-degree angle between those two, because we're looking at the angle up in here between the two. Not a 90-degree angle. So point being, because this angle is more for B than it is for A, the torque is going to end up being more for B than it is for A. So it's looking like choice C here would be our best answer. Choice C is best because we got a 90-degree angle between our radius, our lever arm, and B here. That means theta comes out to be 90. Here, that angle is less than 90, so there's going to be a smaller torque. These two torques are 0 because they're acting along the radius. The angle between them and the lever arm is 0. So choice C looks good on problem 20. Problem 21 looks like this. Three forces are exerted on a disk of radius r. It's free to spin about its center. The magnitudes of the forces are proportional to the length of the force vectors. And F2, force 2, is equal to F3. And F1 is equal to 2F3. What is the sum of the torques exerted by F1 and F2? All right, so the problem for some reason is not showing this on here, but this angle right here should be 30 degrees. We'll get that fixed. So what is the sum of the torques exerted by F1 and F2? So let's look at F1 first. Remember that torque is equal to force, and the force here is just F1. And I'm going to make that be, make sure we know that's a 1. So that's a force times the radius. Well, this is, if we drew in a radius here, that's a longer radius. The radius is of length r. And notice that that angle between F1 and the radius is 90 degrees. Sine of 90 is 1, so it doesn't really matter here. So the torque for 1 is just F1 times r. Now for 2, here's 2. That torque is going to be equal to the force. Here's where it gets a little complicated. F2 is equal to F3. F3, or 2F3 is equal to F1. So here's the deal. Essentially, if F1 is equal to 2F3, F1 is also equal to 2F2, because F2 and F3 are the same, which means that F2 is equal to 1/2 F1. That's the important thing. If we're going to compare these, we've got to compare the same thing. So if we're calculating the torque caused by force F2, let's use a force of 1/2 F1. The radius here is still all the way out the radius, so it's still r. And then times sine 30. Sine of 30 is 1/2. So let's replace that sine 30 by 1/2, which means the torque caused by F2 is 1/4 F1 times r. Now, directions matter here too. the torque caused by force 1 is a counterclockwise torque. It's going this way. And we consider counterclockwise torques to be positive. The force caused by F2, it's going to cause the thing to rotate this way. So it's clockwise. We consider clockwise torques to be negative. So essentially, we've got negative 1/4 F1R plus F1R, positive F1R. So positive F1R, counterclockwise torque, plus negative 1/4 F1R, a clockwise torque. Those add together to be 3/4 F1R. And it's positive 3/4, which means it's a counterclockwise torque. C is what we're looking for there. So that may be one of the more complicated problems that we've done. We're going to look at, I think, another version of this problem on the next one. So let's go to 22. So again, the same three forces, same basic setup. Which two forces exert torques of equal magnitude on the disk? Well, we know that 1 and 2 are not the same. We already calculated those. So we calculated the torque of force 1 to be F1R. We calculated the torque of force 2 to be negative 1/4 F1R. So let's go ahead and calculate the torque caused by force 3. So again, remember force 3 is equal to force 2, and F1 is equal to 2 F3s, which means that F3 is equal to 1/2 of F1. So let's use that 1/2 F1 as our force. And notice that our radius here is only equal to R over 2 because it's this force is applied in the middle of our bigger sphere. So R is 1/2 R, like that. So the total torque, therefore, would be 1/4 F1R. And it's causing a clockwise torque, which means it too would be a negative clockwise torque, which I'm hoping tells you that 3, the torque caused by 3, is the same as the torque caused by 2. So that's telling me that choice B is looking good here. All right, we got a couple more to go. Here's 23. The figure below represents a rod of uniform density. It's attached to a pivot at the right end and has equally spaced lines along its length. The 4 forces shown can be exerted on the rod as indicated. Which of the forces would create the largest rate of change in the rod's angular momentum? All right, so first of all, we need to decode what that means. This is really asking us which one of these causes the biggest torque. Because remember that torque is that. And remember that angular momentum is this. So the thing that causes the biggest angular acceleration is going to cause the biggest change in angular velocity. Bigger torques are going to cause bigger changes in the rod's angular momentum. So essentially, we're looking for which one of these causes the biggest torque. So let's think of each one of these lines as being a meter, some unit of length. So the torque caused by this 130 Newton force would be 130 times 2, or 260 Newton meters. The torque caused by the 60 Newton force would be 60 times 1, 2, 3, 4 units, or 4 meters. So that would be 240 Newton meters. The torque caused by the 50 Newton force would be 50 times 1, 2, 3, 4, 5, 6 units of length, or 6 meters. So it'd be 300 Newton meters. And the torque caused by the 20 would be 20, the force, times 1, 2, 3, 4, 5, 6, 7, 8, times 8 meters, would be 160. What I'm hoping that you see is that the force that causes the biggest torque is that 50 Newton force because it's so far from the pivot point. So our answer going to be C. Bigger torques going to cause bigger angular accelerations, bigger changes in angular momentum. C looks good. All right, here's 24. So this time we have a disc of radius 0.3 meters, free to rotate around its center with negligible friction. A string wrapped around the disc is pulled and exerts a 3 Newton force tangent to the edge of the disc for 2 seconds. If the disc starts from rest, what is its angular speed after 2 seconds? So this is sort of one of those things like you have a push mower where you have the pull start. So you got a rope wrapped around the inside. This would be like our little handle right here. And you pull that thing with a certain amount of force. And it's going to, that force is going to be applied to the wheel. We've got a radius of that wheel, which we know. So it tells us the radius is 0.3 meters. And we want to know the angular speed after 2 seconds. So this is another one of those problems where you've got to use change in angular momentum is equal to impulse. And I keep wanting to put an S there. That's a T. So it tells us that the speed starts from rest, which means the change in angular speed is going to end up being our final speed. So let's solve that for angular speed. So delta is going to be equal to T, delta T divided by I. So the torque is going to be the force, the 3 Newtons, times the radius, the 0.3 meters. And if you look at our picture, our force is going to be applied at a 90-degree angle to our radius. So that's sine 90, which is 1. So it doesn't really matter. So we've got the torque here times the time, 2 seconds. And we're going to divide that by the I. Now here's the thing. In this problem, we don't know the I. They don't give us a formula for calculating the I, which means it's going to be really, really hard to come up with a change in angular velocity. So the best answer here, D. Now there are formulas for calculating those I's. You're not expected to memorize those in AP Physics 1. So here's a problem that looks very, very similar. But this time they tell us that they're going to tell us the formula for I. Actually, it doesn't tell us. So that's exactly the same problem, isn't it? So let's go ahead and I'm going to give you the formula for I. Problem should have given it to you here. The formula for the moment of inertia of a disk here rotating, around a horizontal plane is I equals 1/2 mr squared. And that should be in the prompt of the question. So we're going to need to fix that question. But let's say it told us that I is equal to 1/2 mr squared. So let's go ahead and calculate I for this disk. I is equal to 1/2 times the mass, 0.6, times the radius squared. Radius is 0.3 meters. So if we calculate that out, I'm going to write it up here. I is equal to 0.0270 kilograms times meters squared. Now we know I. And now we can use the same idea we did in the last problem, where we calculate the change in angular momentum is equal to the impulse. Solve that for change in angular velocity. And now just plug in our numbers. Our torque is our force, which is the 3 Newtons, times the radius, force times radius, 0.3 meters, times sine of 90, which is 1, times the time. And it says we apply this force for 2 seconds. Let's divide that by the moment of inertia I, which is 0.0270. And if we do the math on that, that comes up with a change in angular velocity of 66.7 radians per second. And since we started with an angular speed of 0, we started at rest, and it changed this much. This is our final angular speed. So choice D, looking good as our final answer on that one. All right, I think we have one more to go, maybe two. The picture above depicts a solid rod that is fixed to a horizontal surface at pivot point P. So think of this like on the side of a table or something with like a rod sticking out the table. And this thing can rotate along that pivot point. The rod is initially rotating without friction in the clockwise direction. So it's initially going this way. At time t, 3 forces indicated by the arrows of equal magnitude are applied to the rod. Which of the following is true about the angular speed and the direction of rotation of the rod after time t? First of all, let's think about this force right here. This force acts at the pivot point. And when we remember, we know that torque equals F times R. Well, R is 0 because it's at the pivot point. So this thing essentially causes no torque. This one over here is going to cause some torque, but it's small. And this torque is actually pushing it this way in the opposite direction that it was rotating. Finally, this torque over here, this force over here is way away from that pivot point. It's going to cause a big torque. So you got a big torque over here, a little torque over here. These are acting in the opposite directions. So this one is going to cancel out a little bit of this one, make it smaller, but we still have a net torque acting in the clockwise direction. The thing was already spinning in the clockwise direction. So since there's a net torque acting in the direction it was already spinning, it's going to speed up. So its speed is going to increase, and it's going to continue moving the way it was already moving, which is clockwise. So choice B looks like our best answer on this question. All right, let's finish up with practice problem 27. So in this one, we have 3 identical forces, each of magnitude F, and you see those here. They're applied to a stick that rests on a horizontal table. So it's just laying flat on the table. Think of it like a yardstick. At what labeled location on the stick and in what direction, up or down, would a 4th force, also of magnitude F, need to be applied to establish static equilibrium? And you know, static equilibrium means it's not moving linearly. It's also not rotating. It's also in rotational equilibrium. So let's first of all look. This force is trying to make the stick have a clockwise rotation. This one, same magnitude, trying to make it have a counterclockwise rotation. And those guys are the same distance from each end. So this one's 2 units from the right. This one's 2 units from the left. And they're the same magnitude. So these 2 forces and their torques are going to cancel each other out, which means we need a torque that's going to cancel out this guy. Well, this guy is 1, 2, 3, 4, 5 units from the right, 5 units of distance, and it's trying to make the thing rotate in a counterclockwise direction. So we need something that's going to be essentially 5 units from the left, same magnitude. So 1, 2, 3, 4, 5. So that's looking like that puts us at position C. And if we had a force acting like this at position C, it would try to rotate the thing in the clockwise direction, thus canceling out this one. So we need a force at C that's in the up direction to cancel out that, that 3rd force. All right, that's it for today's problems. I hope that helped, and we'll see you in the next unit.